As I have reason to believe I have disintegrated the nucleus of the atom, then this is of greater significance than the war. Quoted Ernest Rutherford after discovering the atomic nucleus. In this video, I'm going to brief you what is a nucleus and what are its general properties. Let me quickly brief what is a nucleus. We all know the fact in this universe everything is made up of matter, and in turn the matter is made up of the smallest unit called atoms. And what are these atoms, the basic units of matter made up of? We know atoms are made up of proton, neutron, and electron. So, when analyzed, there was a region which is highly denser at the center of the atom, and that center part of the atom is called the nucleus. The most of the matter is concentrated at the central part, and that part is called as the nucleus. The atomic nucleus was discovered by Ernest Rutherford in 1911 in his famous alpha scattering experiment. Rutherford was not only able to discover the atomic nucleus in this experiment, he also discovered alpha rays as well as the beta rays. In his alpha scattering experiment, he showed this atom consists of a denser region or a smaller, I mean, consists of a very small nucleus whose diameter is around or whose size is around 10 power minus 14 meters, the very very smaller one, which is surrounded by the orbiting electrons. Okay, what is atomic nucleus made up of? The atomic nucleus, the constituents of the atomic nucleus are proton and neutron. Collectively they are called as nucleons. Protons and neutrons are collectively called as nucleons. We know protons are positively charged particle and neutrons are electrically neutral. How will you write a nucleus? A species of nucleus or a nucleus can be symbolically represented as X, that is the uh, chemical species taken, and ZA. Here, Z stands for the atomic number, that is the number of protons present in that nucleus, and A is the mass number which represents total number of protons and neutrons together, and X is the chemical symbol of the species, and the number of neutrons. If you want to get the number of neutrons, if you do A minus Z, then you will get the number of neutrons present in the nucleus. Let us take a chemical species chlorine, Cl1735. So here Z is 17 and A is the 35. A is 35. So A minus Z equal to N, that is 18. So Cl 1735 contains 17 protons and 18 neutrons. This is how we have to find the number of protons and neutrons present in a nucleus. Then let us move to the general properties of the nucleus. First, let us see what is the nuclear size. So in his alpha scattering experiment, Rutherford showed the mean radius of an atomic nucleus is approximately around 10 power minus 14 meter to 10 power minus 15 meter. And he also established an empirical formula for nuclear radius, which is given by R equal to R naught A power 1 by 3. Here A is the mass number, that is the number of proton, the number of proton plus neutron, and R naught is a constant and its value is 1.3 into 10 power minus 15 meter. Let us calculate the a nuclear radius of a beryllium nucleus Be48. Here A is the 8, that is the mass number is 8 here, and the formula we know R is equal to R naught A power 1 by 3, and we know the value for R naught is 1.3 into 10 power minus 15 meter. Substituting all the values in the formula, 1.3 into 10 power minus 15, A power 1 by 3. This A power 1 by 3 can be written as 2 power 3 into 1 by 3. This 3 and 3 will get cancelled. We will get 1.3 into 10 power minus 15 into 2 will give us R equal to 2.6 into 10 power minus 15 meter. This is the radius of the beryllium nucleus. So using the uh, formula, the formula for the nuclear radius, we can easily calculate the radius for any atomic nuclei. Next, we'll see the nuclear charge. We know the nucleus consists of protons and neutrons. We know, and also we know neutrons are electrically neutral. So the charge on the nucleus is entirely due to the protons present in it. The value of one positive charge is 1.609 into 10 power minus 19 coulombs. So the total nuclear charge is equal to Z times E. Z is the number of protons present. E is the value of the one positive charge. The nuclear mass, we know the nucleus consists of both protons and neutrons. For example, if we take a nucleus has Z protons and N neutrons, the total nuclear mass will be equal to Z times Mp plus N times Mn. So that means we know Z is the atomic number, that is the number of proton present, and Mp is the mass of the proton. So Z into Mp, and N is the number of neutron, and Mp is the mass of the one neutron. So the total nuclear mass will be equal to Z times Mp plus N times Mn. Mass defect. So what is this mass defect? So just now we have calculated what is the nuclear mass. Generally, in practice or experimentally, nuclear masses are measured by mass spectrometers. But the measurements made using mass spectrometer shows that the actual mass, obtained from the mass spectrometers does not tally with the theoretically calculated mass. So the real nuclear mass obtained from the mass spectrometers are always less than the theoretical mass ZMP plus NMN. So but how does this mass differences arises? So this mass differences arises because of the conversion of mass into energy, which we will see later. So the mass difference ZMP plus NMN minus real mass is equal to delta M, and this delta M is called as the mass defect. In all nuclear reaction there will be some mass defect. Then we will move to what is a nuclear density. We all know the nucleus is a very denser material, or it is in a highly compressed state. Generally the nuclear density is calculated as mass by volume. Here nuclear density rho n is equal to nuclear mass by nuclear volume. So putting the nuclear masses, we know it is A into Mn divided by nuclear volume. Since it is in a spherical shape, it is 4 by 3 pi r cube. So in place of r, we can write r naught a power 1 by 3. So substituting all this, you will get rho n equal to 1.816 into 10 power plus 17 kilogram per meter cube. That is 10 followed by 1 followed by 17 zeros. This shows that how dense the atomic nucleus will be. So from this figure or from this number, it is very clear that nuclear matter is in extremely compressed state. The nuclear spin. So both the proton and neutron have an intrinsic spin S equal to half. We know both protons and neutrons are Fermi particle and they have a spin of S equal to half. Packing fraction. Packing fraction is nothing but it is the ratio between mass defect and the mass number. The mass defect is delta M and the mass number is A. So F is equal to delta M by A. So what is the need for this packing fraction? This packing fraction will tell us whether the nucleus is stable or unstable. If the value of F is negative, the nucleus is stable, and if it is positive, the nucleus is highly unstable. Okay. Then binding energy. Okay, we said there is a mass defect. The calculated values of the nuclear mass does not tally with the mass obtained from the mass spectrometer. So there is always a mass defect. So the theoretical explanation for the mass defect can be given using Einstein's equation E equal to mc square. This equation E equal to mc square states where the energy can be converted into mass and mass can be converted into energy. Okay, if in case if you have Z protons and N neutrons in a nucleus, where when they combine together to make a nucleus, during this process some of the mass disappears and this mass is converted into an energy which is given by mc square. This energy is called as the binding energy. The energy required to bind the proton and neutron together to make a nucleus is called as the binding energy. The same energy is required to remove a nucleon, to remove a proton and neutron from a nucleus. This amount of energy we have to give it to a nucleus to remove a proton and neutron from the nucleus. So this energy is the energy required to remove a nucleon is also called as the binding energy. And this binding energy is the key. It plays the key importance because it determines the nuclear stability. We can calculate binding energy as Zmp plus Nmn minus m into c square. So that is delta m into c square. If in case the binding energy is greater than 0, this suggests that nucleus is highly stable, and if it is less than 0, the nucleus is unstable. Here is a very simple problem to calculate the binding energy of a nucleus. Here we are going to calculate the binding energy of the helium-4 nucleus. So helium-4 nucleus has 2 protons and 2 neutrons. We know He24. So there are 2 protons and 2 neutrons. We know the mass of the one proton is 1.00728. So 2 protons, 2 into 1.00728 is equal to 2.01456 atomic mass units. In the same way, let us calculate the total mass of the 2 neutrons. So it is 2 into 1.00866. So it is 2.01732. Let us add the mass of 2 protons and 2 neutrons, that is the total mass of the nucleons, which adds up to 4.03188 AMU. So the mass of the alpha particle, that is the helium nucleus, measured from the mass spectrometers accounts to 4.00153 atomic mass unit. So there is a mass defect between the theoretical value computed and the mass obtained from this mass spectrometers. So hence there is a mass defect of 0.03035 atomic mass units. One atomic mass unit is equal to 931.5 MeV. Hence let us convert the AMU into the MeVs. So it is 0.035 into 931.5. You get 28.3 MeV. So the binding energy of helium-4 nucleus is 28.3 MeV. I hope this video will be useful in understanding the basic nature of the nucleus. Thank you.